Hey everyone, this is Mr. Kabbalah. This is going to be Statistics Unit 8, Section 4 on the distributions of differences between population means and population proportions. Let me know if you have any questions and enjoy.
Okay, so one way to compare populations is to compare the difference in population means or the difference in population proportions. So remember, difference means to subtract, so we're going to be subtracting two means or subtracting two proportions. To make a statistical estimate about the difference between two population parameters, we need to have a sample from each population. Samples may be independent or dependent according to how they were selected. Two samples are considered independent if sample data drawn from one population are completely unrelated to the selection of sample data from the other population. As an example, the one that I can think of is imagine in one growing season picking apples from one bunch, let's say in 2019, and then taking a sample of apples in 2020. Even though we're comparing apples to apples, we're comparing different groups of apples. There's no way to line up the apple from last year to an apple from this year. Whereas two samples are considered dependent if each data value in one sample can be paired with a corresponding data value in another sample. I liken this to imagine in a class you take a pre-test, right? Then you do a lesson, and then you take what's called a post-test. And the teacher might see, okay, how did a sample from here compare to the sample from here, where you can line up one score from one student compared to their score on the post-test after the lesson. So one data point lines up with another data point. So independent samples occur when we draw two random samples, one from the first population, one from the second population. There is no pairing of measurements between the two populations. We should even put in here, I've seen people say they're independent even if there was no attempt made to pair. Dependent samples occur in before and after situations in which the same item is measured twice, so kind of like the student pre-test, post-test. In this section, we'll be concentrating on independent random samples. If we get to it, we'll have a whole section on dependent random samples, but here's a little sketch of what's going on. There's two populations that are in the big circles. What we're doing is we're taking random samples from each of those. So let's, sample one, what we do is then take the sample mean. So we're calling the X bar. The first one is population one. The second one is sample one. So sample mean, population one, sample one. This one, population one, sample two, and so on, all the way down to however many samples you want to take, K, we'll call it. Then with population two, same thing. We take sample one and find its sample mean. Then we take these two sample means and we subtract them to take a look at the differences. So that's what's going on here. That's a little picture. So a note on calculations involving the difference of sample means and, of population means and population proportions. Once we calculate a confidence interval, so that's something like we are 90% sure that the population mean is between 3.5 and 4.5. If we might get bounds in that interval that are both negative, and if both bounds, the lower bound and the upper bound, are both negative, it implies that the first population mean is less than the second population mean. Think of those two numbers. If they are 3.5 and 4.5, we'd get a difference of -1. And that's always going to happen if the second population mean is greater than the first population mean. And then similarly, if we calculate a confidence interval, if both of the intervals are positive, that implies that the second mean is less than the first mean. Okay, kind of the similar thinking as what's up here. If these were reversed, then the first one would have to be larger than the second one to have a positive difference. If we calculate a confidence interval, if bounds are both positive and negative, then we cannot imply that one is larger than the other. In short, the order of the data matters. So it matters that there's population 1, population 2. We're going from 1 to 2 because we need to check to see negative, positive, or both. So keep that in mind as we move forward. All right, so if we want to do a confidence interval for the difference of population means, and we know the population standard deviations, which is not typically likely, then we would follow all these. We would have to make sure we have a normal distribution, so mound shape symmetrical. The mean of this distribution is the difference between those two. You can see that there's a standard deviation. N1 and N2 are the sample sizes of the two populations. The margin of error is the standard deviation times this ZC, which again is the critical value. Right? And it would go something like this. I'm not going to read everything, but basically there's a park, it had a fire. Fishermen are saying that before the fire, fishing was either better or worse than after the fire. They want to compare the two. If you read through this, it gives us a whole bunch of information. We got our sample mean here of 5.2 trout per day before the fire out of 167 reports and a standard deviation of 1.9, whereas after the fire we have a sample mean of 6.8, population standard deviation 2.3, and a sample size of 125. Now we could do these by hand. Also pointing out 95% confidence interval, but actually your calculator does a really good job with what's called two sample confidence intervals. So if we just take a look at the calculator, okay, what we're going to do is we're going to go to stat, we're going to go to tests, and we have a two sample, and what we want to do is a two sample Z interval. The reason why we are using the Z interval is because we know the population standard deviations. If we didn't know the population standard deviations, which we're going to see in just a minute, we would use the two sample T interval. But in any case, two sample Z interval, and then we just have to fill in all this information. We're going to keep it on stats. If we wanted to use data, it's using lists like L1, L2. So you could go that route, but I'm just going to type in the information. This might be what we need to use. Let me just go back here and make sure. 1.9, 5.2, 2.3. Oh, no, I guess I have to change a few things. 1.9, 2.3. All right, so I believe X bar 1, 5.2. That had a sample size of 167. X bar 2 was 6.8. And that had a sample size of 125. And I do have to go back and fix these standard deviations. And one was 1.9. Nope. Yep. And 2.3? Okay, yeah, I guess I was right. All right, sea level, not 99%, but 95% it says in the problem. And we get this, negative 2 point, let's say 1 to negative 1.1. So negative 2.1 to negative 1.1 would be our confidence interval. So what we can say, what does this mean? So this means we can be 95% sure or confident that mu1 minus mu2 is between negative 2.1 and negative 1.1. Now, going back to what I just spoke about, because both of these are negative, we are 95% confident, I'm going to abbreviate confident, that mu1 is less than mu2, which means that we can be 95% confident that the fishing before the fire was worse than the fishing after the fire, because mu1 would have to be less, or 95% sure that it would be less. So that's something we can use to check the population of trout. Now, most of the time, you're not going to know the population standard deviations. So we basically change the sigma into an S. S stands for sample standard deviation. So you can kind of see that here and here in the formula. But again, your calculator does a good job of doing two sample t-tests, because now that we're using sample standard deviations, we're going to use students' t-distribution, which if you haven't watched, I think it was section 3 of Unit 8 on the t-distribution, you could go back and watch that. So how this works, you could read this whole thing. It's about an archaeological dig. What we're going to do is we're going to go to this Google Sheet, and we're on Ireland Ireland artifacts or something like that. In any case, we have two regions, and what we're going to do is we're going to get a sample size. So one way to do that, you could just count it, but you could also do the function count, and you could count how many things are here. So the sample size for region 1, it's lagging a little, 12. Sample mean would be the average of region 1. The sample standard deviation, I'm going to do .s. That ensures that we're using a sample standard deviation formula. And we get those values for region 1. So again, count, you could just count them by hand. Sample, so average. Now make sure, if you're going to highlight like I did, make sure that you don't highlight the sample size as well. Only go to in C17. And then again, I'm going to do the .s one. That's for sample standard deviation. And again, be careful, don't go down into your sample size, sample mean, and whatnot. All right, now I'm going to use those on my calculator. We can do this on the spreadsheet. It gets a little cumbersome. The calculator actually does a better job of it. And then this time we're going to do stat over to tests, and because we're using sample standard deviations, we're going to do a 2 sample t interval. So that's choice number 0. All right, and we're going to fill in all of this. We got the stats, and here we go. We got x bar 1, which is 747.5. the sample standard deviation, which is 170.4, and the sample size was 10, 12. All right, X2, 738.9, 212.1, and 16. Now let's go back to the problem. What size interval does it want? 90%. On your calculator, there is this pooled. That's what you'd use if the standard deviations were the same or relatively the same, which in this one, they're not close, so we're not going to pool it. In fact, in all of these examples, we're not going to pool. It's just a slight difference in calculation. So 485.21 to 731, let's say 732. So let's say 485 to 731. 485 to 731. What does this mean? 90% confident that the inorganic phosphorus, and I'm going to abbreviate phosphorus, levels and I should put in here the difference. Sorry, the difference between the inorganic phosphorus levels is between 485 and 731. Another thing we know, because both of these are positive, we are 90% confident that mu2 is less than mu1. Now the question is asking, I guess it doesn't, at one point I had written something else, but we can be 90% confident that mu2 is less than mu1. That's because both the lower bound 485 and the upper bound 731 are both positive. So another example that we're going to do part on the computer, on the spreadsheet, so companies, foreign revenue, and then we'll go to the calculator. In fact, I might speed things along. All right, so for this one, we get a confidence interval between 12.8 and 23.4. 12.8 and 23.4. What does this mean in the context of the problem? So this tells us, or we can be 85% sure that the difference in population means between, and I think it was tech companies and basic companies, between the types of companies and it was the company's percent foreign revenue. So companies percent foreign revenue is between 12.8% and 23.4%. So that's the difference between the two. Now, because both are positive, that tells us that mu2, the second population mean, is going to be less than the first population mean. On our spreadsheet, the first population were the tech companies. So this is telling us that we can be 85% sure that tech companies have a larger percent foreign revenue than those of the, I think they call them basic companies. So things like tire sales and toys and whatnot. All right, so I'm going to do similar things for um, pro athlete heights and weights. I think the first one's weights and then heights. So try these out and then see if you get the same thing as me. All right, so I rounded these to 40 pounds and 62 pounds. In context, we can be 99% sure that the difference between the population means is 40 to 62 pounds. Another way to put this, we can be 99% sure that NFL players or pro football players have a higher average weight than basketball players. And that's because both of these, 40 and 62, are positive. So mu1 would have to be larger than mu2. All right, now going to the heights. All right, so I rounded these. Our confidence interval, our 90% confidence interval, is from negative 0.43 to negative 0.17. So I'm going to say this 90% confident that mu1 is less than mu2 because both of our bounds are negative, which then tells us we can be 90% confident that the population mean, or let me put it in context, that basketball players are taller than football players, which doesn't surprise me in the least. Now, we can have proportions, and it goes through some of the calculations. The p hat and the q hat, remember, are the point estimates for p and q. P and q are the population proportions, and q being the opposite of p. P hat and q hat are just kind of like the sample proportions and the sample opposite the proportion. In any case, you can see the calculations. But again, your calculator does a pretty good job of this. So as an example, it's a sleep study. It gives us the number in the first group. 49 had dreams with feelings of anxiety, fear, or aggression. In group 2, they did not watch a movie. They just went to sleep. 180 of those folks, and 63 had dreams with anxiety, fear, or aggression. We want a 95% confidence interval. So because we're dealing with a proportion of people, so think of, 49 of 175, 63 of 180. So that's a proportion. So if that's the case, Then we're going to go to Stat, Tests, and we have a two proportion Z interval. So that's choice B, two proportion Z interval. And so it's going to ask us, okay, what's X1? So that's the people who had bad dreams, 49 out of 175. And then it was 63 out of 180. And we wanted, I think it was a 95%. Yep, 95%, 0.95. So it goes from negative 0.17 to 0.03. And what does this tell us now? Because we're using z's, that would be the difference between z-scores. What we can say is that we're 95% confident that we can't tell which population proportion is larger. So really, based on this, we can't tell if watching a movie before going to sleep has any effect on your dreams. That's what kind of this says. We can be 95% sure that that's true. Right, as another example, we've got all of this, a random sample of 316 patients. So this 316, that's going to be our N1. Of these patients, it's found that 259 had no visible scars. That's our X1. 419 would be our sample size of 2, and 94 had no visible scars. So again, here's how you do it on a calculator. Why this is a proportion, it's how many out of a sample. So it's 259 out of 316 compared to 94 out of 419. Those are proportions. So that's why when we do this on our calculator, we would go to a two proportion Z interval. And 259, 316, and 94, 419. And we want 95%. So 0.53 to 0.65. Now, what this tells us is that we can be 95% confident that mu2 is less than mu1. So in terms of this, this means that we are 95% confident that the no plasma compress treatment people that the plasma compress treatment actually helped the scars of the first group more than not receiving the plasma compress treatment for the second group. And we can say that with 95% confidence. Okay, well, hopefully that made sense. Let me know if you have any questions, and hopefully we'll see you soon.